So today's material is going to look at chemical bonding. How do we represent a chemical bond, ionic and covalent bond? What does that look like? What electrons are we sharing? What electrons are we exchanging? And how many electrons are participating? So for this weekend, you have Chapter 7 and 8 homework due on Sunday at midnight. We're going to start Chapter 8 today. We finished Chapter 7 yesterday, looking at ionization energy trends and electron affinity trends. We're in the final home stretch of the course, so really try to get caught up on all the homework, get ahead on all the homework, and try to get an idea or get started on the chemistry in your life assignment that's due at the end of the semester. Also, I'm working on the final exam review guide and the practice exam for the final exam, so that'll be made available as well in the next few days because that's coming up basically in about a week, a little over a week. So we finished last class looking at our trends in ionization energies and electron affinity, and we noticed that all of the metals, all the metals tended to have a low ionization energy. All the metals were over here with a lower ionization energy. That meant it was easy for a metal to lose an electron. Relative to our nonmetals are all up here. Our nonmetals all tend to have a higher ionization energy, which means it's harder for them to lose energy. And the other trend we looked at as well was our electron affinity. Our nonmetals also tend to have a higher electron affinity, meaning they'd rather gain an electron than lose an electron. So why do metals tend to form cations? Metals tend to form cations because they have a low ionization energy. It's easy for metals to lose electrons, a low ionization energy. So what does that mean when we combine metals and nonmetals, right? Metals on the left side of the periodic table have a low ionization energy. Our nonmetals on the right side of the periodic table have a higher ionization energy, so they don't want to lose electrons, and they also have a high electron affinity. They really want to gain electrons. So when we combine a metal and a nonmetal, we make an ionic compound. We make an ionic compound because our metals really want to lose electrons, and our nonmetals, with their high electron affinity, really want to gain an electron. So in an ionic compound, our metal will lose an electron, and our nonmetal will gain that electron. We'll form ions after that reaction, and then those oppositely charged ions will be attracted through electrostatic attraction, making our ionic bond. We've also looked at covalent compounds this semester. Covalent compounds, I said, were formed when a nonmetal bonds with a nonmetal. So something in the upper right-hand corner of the periodic table bonds with something else from the upper right-hand corner of the periodic table. Those make molecular compounds because they form covalent bonds. They form covalent bonds because nonmetals have high ionization energy. So both of those nonmetals that you're combining, they don't really want to lose an electron. They have a high ionization energy, making it hard to remove an electron. On top of that, they both also have high electron affinity, so they want electrons. Combining the two will result in a covalent compound, a molecular compound. When you combine two nonmetals together that both have a high electron affinity and both have a high ionization energy. In that case, it's easier to share electrons than to transfer electrons between those two atoms. So in an ionic compound, how do we determine how the metal and the nonmetal will react, and what does that ionic compound look like? Well, from what we saw last class when we looked at making cations from metals and anions from nonmetals, we can come up with two general statements. The first statement is that metals will lose enough and sometimes all valence electrons to become isoelectronic, have the same electron configuration as a noble gas. So our metals, we're going to lose electrons, we're going to lose our valence electrons in an effort to become isoelectronic, to have the same electron configuration as a noble gas. Our nonmetals are going to do the opposite. Nonmetals will gain the required number of electrons to become isoelectronic, right, have the same electron configuration as a noble gas. So for example, if we look at a metal, we can look at sodium, for example. When sodium goes and forms sodium plus 1, it's going to go from the configuration of 1s2, 2s2, 2p6, 3s1 to the configuration of, after it loses that electron, right, plus an electron, it's going to go to 1s2, 2s2, 2p6, and it's going to be isoelectronic with neon. We can look at chlorine as another example. Chlorine plus an electron to chloride. That's going to look like 1s2, 2s2, 2p6, 3s2, 3p5. I add an electron in, and that's going to become 1s2, 2s2, 2p6, 3s2, 3p6, adding in an extra electron. Right, the p orbital can hold a total of 6, and I'm isoelectronic with argon. So let's take a look at that reaction between sodium and chlorine to form sodium chloride. Sodium, the metal, loses 1 electron, becoming sodium plus 1. Chlorine, the nonmetal, will gain that electron, becoming chloride minus 1. Here's sodium on the periodic table, right? I've got 1 valence electron I can lose, becoming isoelectronic with neon. And here's chlorine on the periodic table. Chlorine gains that 1 electron from sodium, becoming isoelectronic with argon. So for that ionic bond to form, we need that transfer of electrons. And so we can look at them as each individual half reaction. Sodium going from sodium 0 to sodium plus 1, losing an electron. Chlorine 0 gaining an electron, becoming chloride. But essentially that sodium is transferring its electron to chlorine, forming our sodium and our chloride. And then the next step, our ionic bond will form between those two oppositely charged ions. And again, just writing out that what that would look like with respect to the electron configuration. I'll do the condensed configuration this time. Sodium would be neon 3s1, and chlorine would be neon 3s2, 3p5. Chlorine gains that electron. Sodium is going to lose an electron, so it's going to become neon just plus, with respect to its electrons, plus 1 electron. That 1 electron is transferred to chlorine, so chlorine is going to go to an electron configuration of neon 3s2, 3p6, essentially isoelectronic with argon when we have that reaction take place. So we need a better way to kind of think of these representations of electrons, the electrons we're transferring during these ionic reactions. And that's where Lewis electron-dot symbols really help. Essentially, these symbols are just a representation of the valence electrons around an atom. Where I'm going to represent each of these valence electrons as a single dot, where each valence electron is represented as a single dot. So if I take a look at sodium, sodium would be 3s1, magnesium is 3s2. Aluminum would be 3s2, 3p1, and then I added an electron in, 3p2, 3p3, 3p4. What does that look like with respect to a Lewis dot diagram? So I've got one valence electron on sodium. That would be its Lewis dot diagram. Magnesium, I have two valence electrons. This would be the Lewis dot diagram for magnesium. Aluminum, I have three valence electrons, right? So my Lewis dot diagram would look like this. Silicon, I add in one more, so I've got four valence electrons, and I'd have four dots around that atom. Now with phosphorus, I add in one more, that's group 5. Now I can pair up those electrons. There's my 5 valence electrons. Sulfur, I add one more. And there are my 6 valence electrons. Chlorine, I'm going to add one more. So there's 1, 2, 3, 4, 5, 6, and 7. So there's my Lewis dot symbol for chlorine. And then argon, I gain one more. Now I have a full octet. I'm going to have 8 valence electrons around argon, my noble gas. There's 6, 7, 8. So now we can use these Lewis dot diagrams, these Lewis dot symbols to represent how many valence electrons I have, how many valence electrons I have to lose in the case of a metal, or how many valence electrons I have space for to gain those valence electrons in the case of a non-metal. So let's just take a look at how we can use these Lewis dot structures to come together with a formula and understand how a metal and a non-metal will react to form an ionic compound. And so we're going to take a look at magnesium fluoride, the Lewis dot symbol for both magnesium and fluorine, and to look at how we can understand magnesium fluoride forming. So magnesium has 2 valence electrons. Fluorine has 7 valence electrons. 3, 4, 5, 6, and 7. And then here's my other fluorine, 1, 2, 3, 4, 5, 6, and 7. So basically we can look at that as fluorine has a vacancy. It can gain one more electron. This fluorine as well also has a vacancy. It can gain one more electron. We're going to react in a way to become isoelectronic with a noble gas. So fluorine wants to gain one electron, becoming isoelectronic with neon. Magnesium has 2 valence electrons. It wants to lose those 2 electrons. And so what we can imagine, magnesium is going to transfer 1 electron to the vacancy in this fluorine. It's going to transfer the other electron to this vacancy in fluorine. And so we end up making, right, magnesium loses both of those electrons. It's going to form magnesium 2+, and I'm going to form my fluorine, my fluoride. So 1, 2, 3, 4, 5, 6, and 7. And my 1, 2, 3, 4, 5, 6, and 7. And then I can't forget, here's the electron, right? The red electron that came from magnesium. So I've formed my fluorides at -1 each by gaining an electron from magnesium, and I've formed my magnesium 2+ by magnesium losing both valence electrons it had, 1 to each of the fluorines. Now, all 3 of those are isoelectronic with a noble gas, either through losing or gaining valence electrons.